¿Qué onda?
Dale, ¿se nos escucha?
Sí, se escucha perfecto.
Gracias.
Se escucha bien, sí. Hola, ¿qué tal? ¿Se escucha? Perfecto.
Sí se
Pues
escucha.
muchas gracias. Muchas gracias por acompañarnos en el último slot del evento del Lanmr la edición 2023. Eh, y bueno, pues sí, entiendo que todos los que estamos de momentos entendemos castellano, entonces pues dejo a consideración de los próximos presentadores, ahorita los presento, si quieren que sea en inglés o en castellano, sin ningún problema. Eh, bueno, si están de acuerdo, vamos comenzando. La primera sesión de hoy está titulada Meta-Inferential Tableau in the Menu Value Setting. Los autores son Ailén Melissa Babosa Castro, Agustina Borse, Bruno Darre, Ariel Rufé y Joaquín Toranzo Calderón. Em, Entiendo que va a presentar a Ailén, Ailén, perdón. Adelante, todo tuyo.
Hola, yo preparé la presentación en inglés. No sé si les lo prefieren dado que va a quedar en YouTube o en español, es lo mismo, no sé. Como
Sí,
ustedes me digan.
depende de ti. Sí, para nosotros es igual.
Ok, entonces, en inglés, vamos a practicar. All right, so, sorry. So thank you, Ismail. I'm here with my co-authors. Uh, so the aim of okay, sorry. So the aim of this talk is to provide a general recipe to build our tableaus. Yes, but for meta-inferential logics, and we will be based on tableaus for inferential logics. Um, to differentiate us of different types of frameworks. We'll be working with set frameworks, but and also with strong clean evaluations. But that shouldn't be a constriction. That needn't be that way. So we could also have rules for different schema evaluations and also for set formula frameworks, right? But I'll give my talk on the with multiple conclusions framework, right? So this is my plan. I will speak a little bit of, give a brief introduction on meta inferences and why this work came up to be. I will talk about semantics, tableaus, and I will focus later on the case of strong cleaning. Papi. Sorry, I thought there was a question. So yeah, later on I will give a final remarks and speak a little bit more about specific case and how we solve that. Okay, so for the introduction, usually a logic has been characterized as a set of inferences. And some people, Barrio, Pailos, and Smook, for example, have challenged this view, right? So whenever we define a logic, what if we take into account meta inferences, which are, I will define them later, which are inferences of inferences and so on and so forth. And this idea has given rise to plenty of meta-inferential logics, substructural logics, and etc. Right? So, as I said before, meta-inferences are just inferences between inferences or even meta-inferences. We have different levels. And we say that, I am assuming that you can see my pointer. This is a meta-inference, right? And this gamma are the premises, and this delta are conclusions. And those are sets of meta-inferences of a level downward, right? Whenever this is 1, then gamma and delta are inferences. Whenever this is 0, the whole thing is an inference, right? So a logic is a set of valid inferences, meta-inferences, and meta-inferences, so on and so forth. Okay, so valuations, as usual, we'll give a pretty standard definition. It's a function from formulas to a set of truth values. This is the capital V is the set of truth values. Again, we'll be working with strong cleaning. And formula satisfaction is defined this way. So evaluation Vx satisfies, right? Depending with according to standard or a truth value or whatever you take here. Satisfies a formula A if and only if the evaluation of the formula is in that standard, for example, right? And for the meta-inference satisfaction and inference satisfaction also, evaluation Vxy satisfies an inference, this type, if and only if Vx satisfies every premise, then Vy satisfies some conclusion, right? Okay, so later on has been developed these 4 mixed consequence relations, right? Which I'm not going to dwell too much into it, but depending on if your truth values you're taking into account are strict or tolerant, then you have 4 different consequence relations. For example, the SS satisfaction says that if every premise take the value 1, then some conclusion needs to take value 1, and that is SS satisfied. Okay, and then we have TT satisfaction, ST satisfaction, and TS satisfaction. The thing that changes for the other ones are the values that we take into account, right? Okay, so As I said before, we'll be taking into account strong cleaning valuation schemes, right? But our framework shouldn't or needn't be restricted to those. We could have rules for weak cleaning logics, and I will later repeat this. So based on these notions of satisfaction, we can then define inferential logics, and even more, we can go to meta-inferential logics, right? So this inference is Vxy valid if and only if every valuation is in Vxy satisfies, right? So we have mixed inferential logic else, which are determined by a set of Vxy valid inferences, as we said before, and we will sometimes identify or talk about logics in the name of the standards of satisfaction, okay? So given two inferential logics, then the meta-inferential logic that L, for example, which is composed by L1 and L2, is defined as in the next manner. So this is a meta-inference of level 1, and this is valid in that logic if and only if a valuation that satisfies the premises in gamma is according to L1, right, the first one. Then it also satisfies some conclusion in delta according to the second logic, right? And this can be generalized for every level. We don't need to speak of meta-inferences only, at least, but we could also speak of meta-inferences, so on and so on. Okay, so Carlos, here are what like the principal topic of the talk. So far, we have been given a more theoretic presentation of what a meta-inferential logic is, on how can we have an approach to them. And we also know that a logic, since the different approaches that in the literature to meta-inferential logics, we know that a logic in general is the union of the whole levels, right? We know that this means that we cannot be silent regarding the validity of any level of meta-inferences, right? And we will assume also that the meta-inferential logics of a level, suppose n, will only determine that same level, right? So let's get into the tableaus. So as I said before, tableaus are usually introduced in the set formula frameworks, but we will, for this talk, specifically focus on the set framework, right? And this is a node where alpha is either a formula or a meta-inference or an inference, and X is a standard. And what is a standard? So we have the set of truth values, and then X is, if it is inside the subset, sorry, if it is a subset of the truth values, then this is a level 0 standard. Suppose that X is a level n standard, then the complement of X is also a level n standard. And what the third point says is that suppose that X is a standard and Y is a standard of level n, then whenever you put them both together, like X, Y, you have a standard of a level above, right? Like S is a standard, T is a standard, ST is a standard of a level above. So for our tableaus, we have two kinds of rules. We have the general rules and the particular rules. We will first talk about the general rules for inferences and meta-inferences, and then we will talk about the particular rules, and those are for the specific case of strong cleaning logics, right? So we'll start with our initial list. Suppose we want to prove this in a meta-inferential logic of level n with these standards, and then we start with this node, right? where X and Y are the standards that define the logic of the level before, right? So X is for gamma, Y is for delta. Then we apply the first rule, which is inf 0. We just have to make a list of, if we start with this node, right? Then we have to make a list of all the premises and conclusions, where the premises take the value, the first value, and the conclusions take the complement of this value, right? Suppose we don't have this, we take this value for our premises, and this value, we take the complement for our conclusions, right? In one, what tells us is, okay, you can see that we have no line above the standards. What we need to do here is the opposite. We put the complement for the premises and the standard for the conclusions, right? So the rule of complement is quite, I was about to say standard, but it's not unusual. We have the A, for example, takes this standard, which is the complement of X. What you do is you grab your whole bunch of values, truth values, and then you remove X from that set, right? The intersection, well, it's quite easy to see. And well, the intersection rule will be quite important for the closure of the trees. So this is quite important here. And the singletons, which is this formula takes all the values in the set, right? So the main idea is that once we have applied all the general rules for meta inferences, then we go to applying particular rules for inferential logics and also general rules for formulas, right? And so our closure deal is branch in a tree is, you know that tableaus are trees. So a branch in a tree is closed if and only if this happens, right? So A has the empty standard, okay? Otherwise, it remains open. A tree is closed if and only if every branch is closed. Otherwise, it remains open. And whenever we have an open branch, we can have a counter model, which is quite standard again. Suppose we have P and we give it a value that has this standard, and this should be a node in our branch, right? If there is no such node, then it can take any value of our set of values, truth values. So we want to have a sound and complete calculus, and that's why we need to deal with the emptiness on the right. So we have two ideas in order to do so. We can add this closure condition, right? Which means that a branch closes a node if this happens, and also premises and conclusions are empty. And a way to do so is, suppose we have this node, but on our premises, we have this inference, okay? So, the meta-inferential logics that we are taking into account are built on strong cleaning models. I won't get into the truth tables, but know that our rules will represent those truth tables, right? And also, we know that suppose we have this SK evaluation, then K3, we know that this is valid in K3 if and only if every evaluation SS satisfies it. For LP, it is the case that this is valid if it's TT satisfied. For ST, ST satisfied, TS, TS satisfied, right? And we can also define meta-inferential logics by distinguishing these standards for premises and conclusions, and that's not exactly new. So we know that we have standards such as TSST, TSS, and so on and so forth, right? Okay, so representing the strong cleaning matrices, we have these particular rules, right? Which are, for example, for the conjunction, this will be seen later on in an example. We have our conjunction. Suppose we have A and B, and this is true, then A and B are true. If A and B are have the value 1.5, then it is the case that one of them has a value 1.5 and the other one has a value 1 or 1.5, right? If the conjunction is false, then some of them is false. Okay, so for the negation, what happens is 0 and 1 are switched, and for the intermediate value, what happens is that the negation doesn't change the value exactly. Okay, so suppose we want to, give me a second, we want to prove meta explosion in TS, for example. Sorry, I am having trouble with, okay. So suppose we want to prove meta explosion in TS. So we start with our initial list. We have meta premise, our meta conclusion, and this is an inference, this is an inference, and this is a meta inference, right? So we put our meta premise, let's call it, and this satisfies the value TS. Our conclusion should be the complement of ST, as we said before. And again, here we apply the same rule, and Q should have the value, the complement of T, right? Then we apply the complement rule, and we know from here that, again, this satisfies S, right? Because we apply the other rule. And also, if given the strong cleaning schema, we know that if this is satisfied by a strict, is strictly satisfied, then what happens is that P is 1, has a value 1, not P has also the value 1. And what happens here is that we apply the rule of negation and the intersection, right? We have P, and this is empty, right? So this branch is closed. Okay, so the tree is closed, and that's it. This is valid. In this case, I'm not going to explain the whole thing, but you can see that there are branches that remain open, right? And this is our counter model, because P here takes value 1, 1.5. Here it takes value 1.5. Sorry, here it takes value 1.5, and here it takes value 1.5. And there's no empty intersection between those two. So the branch remains open, and then the tree is open. And this is not valid for STST, right? Okay, so some or many advantage of our presentation is that it is completely general. We here didn't get into the set formula framework, but if we change some of the rules, then we can accommodate that. And we also provide general rules independent on the schema or the set of valuations. You know, what needs to be changed for those cases are these type of rules, right? So you change the rules for the conjunction, the negation, whichever you need to change, but the general rules are not a problem for this. Okay, so another benefit that this type of presentation has is that it doesn't add any vocabulary, any new vocabulary to the object language. And also, whenever we can provide operational rules, what I said before, for a schema, suppose we cleaning, one for each connective and truth value, then we just add it to our general rules, and this is a meta-inferential calculus, okay, with tableaus. So I don't know how much time do I have, but I think I have some. So yeah, we know by the literature. I won't take too much time with this. We know by the literature that there have been uh, advances into ST and TS hierarchies, right? So we can develop like a system called ST omega and TS omega respectively, right? And given this type of tableaus, we could just wonder whether some meta-inference of any level is valid in this type of systems, ST omega and TS omega. We just need to build the tableau for that, right? However, I mean, the main idea is that we want a proof system to be able to cover all the levels of the hierarchy. These type of authors and many others have claimed that a logic determines the lower and the higher levels. Whenever what we do for this type of problems, well, not problems, but for these times, what we do is have this type of rules, the lifting and the lowering, which allow us to go to upper and downward levels, right? So lifting is just we add a standard, and lowering just means, okay, get the lower standard, okay? And that could be uh, easily done for ST omega and TS omega, given their representation of those systems. Okay. So our advantage, or at least the advantage we saw for using this type of rules, the lowering and lifting ones, is that we can start with a calculus for an inferential level, suppose, and then we can define different logics going upwards, or even if you're in a meta-inferential level, you can go downwards and so on and so forth. So what we did is that we can also give these type of rules in a more general form, right? By allowing applications of them to any standard, X and Y, right? And we can also treat premises and conclusions of different levels. The main problem that we see here is that it depends on recursion, right? So the fact is that the hierarchy of these types of logic, ST and TS omega, are defined recursively, right? And if that's not the case, then lowering and lifting wouldn't work, right? So that's it. Thank you.
Okay. Thank you, Elaine, for your presentation. It is very interesting work. Now, we have time for some questions. So if you have a question, you can raise your hand here in the Zoom interface. Yes, Alejandro, please go ahead.
Thanks a lot for the presentation. It was really interesting. You can hear me, right? I think that you can hear me.
Yes.
Okay, perfect. So should I change? I think that now we have people that don't speak Spanish, so I guess we should keep in English. Anyway, so my question is, I really didn't get why you need a rule per each value of your logic.
Sorry, can you repeat that one? Because in
Yes.
our computer, in the computer, we can hear you, but we can hear you from the next room.
Yeah, well, I mean, with the echo, but let's try it. Okay, just a second. It's my question is that can you go back in your slides? You have a rule per each value in your logic, right? I mean, in the case of the strong Kleene schema, you have a rule per each value. So I haven't understood why you need that to be so, because I mean, as you know, you can work with signs, and so you can reduce the number of your rules substantially. But and I wonder why you are using a rule per each a rule per each value of your logic. Here you have, for example, in the rules for negation. I don't know what slide it is, but it is back in your presentation. Yeah, there you have for each value of your logic you have a rule, right? And I wonder why that's the case. If you cannot reduce the amount of rules using signs, you know, like Alafitting or Hanle, they have worked on this, and also Marcello D'Agostino. Anyway, it's I wonder why you have this kind of rules, and if at some point we already discussed this. I mean, one day, and somebody told me that it is related to the when you have the case of mixed logics, but I don't know if I understood properly.
Okay, so in this presentation, we just wanted to give like the more general version of the tabular systems. So the idea is that it's relatively easy to come up with rules for every connective and a single truth value. So this is like the more elegant presentation. We know that we can give more efficient rules and reduce the number of rules, or give more efficient rules if we wanted to do so. But the aim of this talk was to just give a general and elegant presentation that is easily generalizable to as many systems as you want, and as many schemas as you want. So yeah, and we know that especially the singleton rule is kind of bad computationally because it forces you to branch a lot in places where perhaps you shouldn't branch, or if you give like more fine-tuned versions of the rules, you wouldn't need to open new branches. But again, it's just a matter of elegance in the presentation and of generality and the possibility of extending these systems. But yeah, we do need to work on that, on more efficient implementations, for example. Thank you.
Thank you. I don't know if I can ask something else. It's a
Go ahead.
can I? Yeah.
Yes.
Oh, okay, perfect. Yeah. It's actually I was right now I was not thinking about efficiency because as you know, like the rules that the meta inference rules where you split your original problem into their components. It's in branches as many times as you have. I think that premises, no, in the at the meta inference level. So it is way. I mean, I don't remember what it should be. Yeah, that one. Yeah, that one. It's I mean, the branching there is a problem for implementation, but just in a not thinking about computational aspects, but just focusing on proof theoretic aspects. I don't know about if it is elegant or not, but still I wonder why you need a rule per each value of the logic, right? Because it's even if it is linear, it seems a bit odd, no? Like having I mean, you're sort of reproducing the truth table. So it's in some sense you are sort of working with truth tables in the shape of tableau. So yeah, it's more a curiosity, but it's really interesting. I will keep an eye on this. Thank you.
Okay, thank you.
We have another example to show. Imagine that you have not one of these negations, but a post negation that in a way emulates a shift value. So if you have a formula with value 1 this connected will give you 1/2, and if you have the value 1/2, it will give you 0, and if it has value 0, it will give you 1. It would be not that straightforward to give a rule with just signs. Perhaps there is, and we don't know yet. But as Ariel was saying, the plan was to give an example to show the generality of this framework. And for example, we can show you that you can have many rules for different systems. This is a very weird system with 4 values, where negation, again, can have the thing that you are saying, but together with the other rules, it would be weird to have a sign alone instead of having the same kind of tags that the other rules. Is that okay as an answer?
Yeah, sure. It's I'm just curious, and but it was clear enough. Thanks a lot for the clarification.
Okay. Thank you very much for the questions and the answers. So let me continue with the program, please. And the following talk is by Agustina Borsi and Martina Ciratu. And
Yes.
okay.
Yo voy a dar la charla. ¿Puedo darla en español?
Sí, claro, sin
Sí,
problema.
por supuesto, perfecto. Hablé con Martina, ella no es hablante nativa de español, pero me dijo que no hay problema, solamente hagan las preguntas en inglés, ¿puede ser?
Claro, sin problema.
A ver. Sí, bueno, justamente. Mientras las preguntas sean en inglés, el trabajo está presentado, las diapositivas en inglés y yo voy a decirlas en español, solo para que el formato Zoom sea menos hostil para todos.
De acuerdo, por supuesto.
A ver.
Ok, entonces, bueno, el título de la presentación es Non-Monotonic Weak-Linear Logics,
Sí.
por Agustina Borsi y Martina Ciratu.
Sí.
Pues puedes comenzar cuando quieras.
Sí. Bueno, primero quería comenzar con una breve presentación de qué son los sistemas Wikilini, y después voy a decir más claramente cuáles son las metas del trabajo. Entonces, vamos a trabajar con un lenguaje proposicional y con la negación, la conjunción y la disyunción. Lo particular de las tablas Wikilini o de las operaciones Wikilini en comparación, por ejemplo, con las Strong-Lini, es que el valor intermedio se comporta como un elemento infeccioso o absorbente. Después, este es el álgebra subyacente de estas lógicas, son semi-birretículos involutivos, no es muy importante, lo importante es tener en cuenta que hay un orden que es para la conjunción y hay un orden que es para la disyunción. La conjunción se define como el mínimo del orden que está a la izquierda y la disyunción como el máximo del orden que ven a la derecha. Un hecho conocido sobre estas lógicas es que como el valor intermedio se comporta de manera infecciosa o absorbente, entonces cada vez que una variable proposicional tenga el valor intermedio, cualquier fórmula en la que aparezca también va a tener ese valor. Se llama el principio de contaminación sí. Sobre este esquema de evaluaciones podemos definir dos relaciones de consecuencia según el conjunto de valores designados que elijamos. Entonces, para consisten Wikilini se define como preservación de 1 o un medio, o sea, preservación de no falsedad, y su contraparte para completa, o Wikilini para completa, se define como preservación de verdad, preservación de 1. Entonces, la primera lógica es una lógica paraconsistente, en el sentido de que el principio de explosión es inválido, y la segunda es una lógica paracompleta, en el sentido de que la ley de tercero excluido es inválido. Pero además tienen otras invalideces famosas, por ejemplo, en el caso de paraconsistent Wikilini, falla eliminación de la
conjunción o simplificación, ¿sí? El contraejemplo está dado por la evaluación que asigna a A0 y a B un medio, mientras que en la Wicklini para completa falla adición o introducción de la disyunción, y el contraejemplo está dado por el caso en el que A es 1 y el B es un medio. Un dato más sobre estas lógicas es que la coma metalingüística no se comporta como las conectivas en un lado del secuente. Entonces, por lo general, la coma en una inferencia, la coma metalingüística puede leerse de dos maneras. Puede ser vista como una conectiva enearia, como una conectiva asociativa binaria, como una conjunción del lado izquierdo, del lado de las premisas, o como como disyuntos del lado derecho. Después, esta equivalencia es evidente por el hecho de que la mayoría de los sistemas que admiten múltiples conclusiones validan esta metainferencia de acá, donde gamma y la conjunción es el resultado de conjuntar premisas, y delta disyunción es el resultado de disjuntar conclusiones. Bueno, en estas lógicas, para abreviar decimos lógicas Wicklini, la correspondencia o esta equivalencia entre la coma metalingüística y las operaciones del lenguaje objeto falla. Entonces, por ejemplo, para consistent Wicklini no es el caso que si una inferencia con múltiples premisas es válida, implica que esa misma inferencia, pero con las premisas en una conjunción, sea válida. El contraejemplo está dado por este caso. Entonces, esto lo que demuestra es que las comas no descargan premisas libremente, pero las conjunciones no descargan conjuntos libremente en estas lógicas. Y lo mismo con o dual para la otra, para completar. Bueno, ahora sí, la meta o el objetivo de esta charla es explorar variantes subestructurales de estados lógicas donde la correspondencia entre la coma metalingüística y las conectivas del lenguaje objeto se vea restaurada. Vamos a llamar a estos nuevos sistemas lógicas uniformes o lógicas Wicklini uniformes. Entonces, nuestra estrategia para hacer esto es dejar las tablas como están, las conectivas como están, pero cambiar la manera en las que se juntan, digamos, las premisas y las conclusiones, y esto lo vamos a hacer dando una definición alternativa de la relación de consecuencia lógica en estas lógicas. Entonces vamos a dar un sistema de prueba para las 4 lógicas que vamos a presentar acá, y al final vamos a presentar una serie de motivaciones filosóficas para trabajar con estos nuevos sistemas que van a ser no monótonos. Bueno, les presento las lógicas uniformes primero. Entonces, como dije, estas lógicas van a ser tales que las premisas se van a juntar de acuerdo con la conjunción del lenguaje objeto y las conclusiones con la disyunción del lenguaje objeto. La forma que vamos a usar para definir esto es apelando al mínimo y al máximo de los órdenes que mencioné al principio. Entonces, una inferencia es válida en la versión uniforme de para consistent Wicklini si solo si el mínimo de las premisas no es 0, entonces el máximo de la conclusión, el máximo del orden de la disyunción, no es 0 tampoco. Y eso, para el caso en el que las premisas y las conclusiones sean finitas, significa que si la conjunción de las premisas no es 0, entonces la disyunción de las premisas no es 0. Y algo análogo sucede para el otro caso. Entonces, estas dos lógicas uniformes son subsistemas de los sistemas originales. Entonces, para consistent Wicklini uniforme es un subsistema de para consistent Wicklini, y este es el ejemplo, es un ejemplo que muestra por qué, ¿no? Entonces, como la coma ahora se comporta como una conjunción del lado izquierdo, va a suceder que P, Q implica Q es válida en para consistent Wicklini porque es una lógica tarskiana. pero que P, Q implica Q no es válida en su compañero uniforme, digamos. Bueno, es fácil ver por este motivo que ambas lógicas son subestructurales. En un caso, en el primer caso, falla weakening a la izquierda y en el caso para completo falla weakening a la derecha. Esto es una manera breve de caracterizar el conjunto de inferencias válidas de estas lógicas. Entonces, por ejemplo, en el caso de weakening para completa, la de abajo, una inferencia es válida en weakening para completa uniforme, si solo si es válida en weakening para completa original, y además se cumplen una de estas dos cláusulas. Entonces, lo que estas dicen es que o bien el conjunto de las variables que aparecen en la conclusión son un subconjunto de las variables que aparecen en las premisas, o que las premisas son o contienen antiteoremas. Bueno, a continuación voy a presentar un cálculo de secuentes para cada una de las lógicas que vimos hasta ahora. Entonces, primero voy a presentar un cálculo para las originales, para consiste weakening y weakening para completo. Y esto se obtiene siguiendo un método, pero además apareció en la tesis no publicada de Bruno, que está por acá. Sí. Y una vez que tenemos esto, ya podemos dar un cálculo para sus contrapartes uniformes, restringiendo las reglas de monotonía. Entonces, sean FITSI fórmulas y las letras griegas mayúsculas conjuntos. Ambos cálculos para consisten weakening y para completa tienen las siguientes reglas, comparten las mismas reglas estructurales. Entonces, identidad, weakening y corte aditivo. Estas son las reglas operacionales para consisten weakening. Entonces, por ejemplo, lo que hacen estas reglas, primero, hay que notar que son reglas impuras en el sentido de que, por ejemplo, hay reglas que introducen dos conectivas a la vez, ¿sí? Las reglas para las conectivas negadas. Y aparte, lo que tratan de hacer es reproducir las condiciones de verdad que se ven en las tablas para las conectivas. Entonces, la introducción de la conjunción a la derecha dice algo así como que ambos FIT-sí son designados o uno es no clásico y el otro es falso. Y algo similar en el caso para completo. Entonces, la disyunción a la derecha dice que al menos un disyunto es verdadero o no, y ninguno es no clásico, por ejemplo. El cálculo de dos lados para sus contrapartes uniformes se obtiene reemplazando las reglas de weakening que son problemáticas. Entonces, por ejemplo, en el caso de para consiste en weakening uniforme, removemos la regla de weakening a la izquierda y la reemplazamos por estas dos reglas. Estas dos reglas lo que hacen, si las ven bien, es reproducir los resultados de caracterización que di antes. Entonces, por ejemplo, en este caso, lo que dice es que si probamos que delta es un teorema o es teoremático o contiene un teorema, entonces podemos agregar cualquier conjunto gamma de premisas. O en el caso de weakening con la restricción lingüística de inclusión de variables, lo que dice es que podemos usar weakening a la izquierda siempre y cuando las variables de la fórmula que introducimos aparezcan en el conjunto de variables de la conclusión. Bueno. A continuación me gustaría dar una serie de, ya presentados los sistemas, me gustaría dar una serie de motivaciones filosóficas de por qué me parece interesante trabajar o estudiar estos primos subestructurales de estas lógicas. Entonces, en varios lugares de la bibliografía se puede ver que el estatus de la conjunción y la disyunción en lógicas infecciosas como conectivas lógicas o como conjunción lógica y disyunción lógica fue cuestionado, y hay buenos motivos para esto. Uno un primer motivo podría ser que invalidan reglas de inferencias que uno por lo general consideran constitutivas del significado de la conjunción y la disyunción. Entonces, el hecho de que para consistent with Clini no valga la eliminación de la conjunción lleva o ha llevado a gente a pensar que no se trata de una conjunción, el operador que usamos como conjunción en esa lógica no es una conjunción en serio. Esto para mí es discutible porque si cambiamos la relación de consecuencia lógica, eso deja de valer. Entonces realmente no es algo que está en las tablas, sino que capaz depende más de la relación de consecuencia que uno elija. Y un segundo punto, quizás un poco más fuerte, de por qué se ha puesto en duda el estatus de estas conectivas, es que tienen unas condiciones de verdad y de falsedad muy particulares. Entonces, es muy común escuchar decir cosas del estilo como que la conjunción es disyuntiva o que la disyunción es conjuntiva, y es porque si nos ponemos a ver las condiciones de verdad o de falsedad de estas conectivas, lo que vamos a ver es que, por ejemplo, en el caso de la conjunción en para consistent with Clini, las condiciones de verdad se definen con una disyunción. Entonces, lo que dice las condiciones de verdad para la conjunción es que una conjunción tiene valor designado en para consistent with Clini cuando o ambos son designados o uno es no clásico y el otro es falso. Los conjuntos. Bueno, y esto llevó a varios autores a decir cosas como que acá puse dos ejemplos. Si uni llama a la conjunción de para consistent with Clini una disyunción disfrazada, y Damián y Hitoshi concluyen en un trabajo que la disyunción de las lógicas infecciosas en realidad no es una disyunción. Pero me parece que hay un tercer motivo por el que hace ruido estas conectivas en la comunidad lógica, no sé, y es un poquito distinto a los dados hasta ahora, y tiene que ver más con el debate inferencialista. Entonces, si retomamos la posición, por ejemplo, de Costa Doyen, para él las constantes lógicas, o un criterio para definir qué es una constante lógica, es que los operadores del lenguaje objeto reflejan ciertas propiedades estructurales de la relación de consecuencia lógica. Entonces, en las palabras del autor, lo que dice es que cuando las constantes lógicas son introducidas en un cálculo, sirven de punctuation marks, de signos de puntuación, en el lenguaje objeto que representan ciertos rasgos estructurales de la relación de consecuencia. Entonces, las reglas operacionales no serían más que ciertas traducciones de cosas que ocurren a nivel estructural, y es lo que ocurre a nivel estructural lo que da cierto significado a las constantes lógicas. Entonces, dado que la equivalencia que mostré al principio falla en estas lógicas, esto es un indicador, o lo tomamos como un indicador, de que la conjunción de para consistent with Clini y la disyunción de su contraparte para completa no pueden ser analizadas en términos estructurales, ya que no son intercambiables con la forma en que agrupamos las premisas y las conclusiones. Entonces, siguiendo esta visión de las constantes lógicas, las constantes, los operadores lógicos de estas lógicas no serían realmente constantes lógicas. Está como en juego o en jaque la logicidad de estos operadores. Sin embargo, en los sistemas nuevos que presentamos, las tablas permanecen igual, son las mismas conectivas, solamente que ahora sí reflejan rasgos estructurales. Entonces, en los nuevos sistemas que presentamos, los sistemas uniformes, escapan de esta consecuencia indeseable. Y un segundo motivo que me parece interesante mencionar para trabajar con estas lógicas que presentamos no monotónicas es que las mismas razones que se suelen usar para citar, para introducir en el lenguaje un tercer valor infeccioso, son esas mismas razones también pueden usarse para motivar que la coma se comporte del mismo motivo. Entonces, todas las motivaciones filosóficas que otros autores citaron a favor de estas lógicas son también motivos filosóficos que uno puede seguir para trabajar con una con una coma infecciosa, digámosle. Entonces, por ejemplo, si queremos entender la validez como inclusión del contenido, inclusión de variables, si queremos modelar la lógica del sinsentido o representar la lógica de programación o de faulty programming, todos esos motivos que se dieron en la bibliografía también pueden citarse acá mismo para ir un paso más y también tener una coma que se comporte del mismo modo y no solo operadores en el lenguaje objeto. Bueno, conclusiones y trabajo futuro. Lo que hicimos en este trabajo fue presentar dos maneras en las que es posible restaurar la equivalencia entre la coma metalingüística y los operadores del lenguaje objeto en las lógicas Wikini. Dos, digamos, caminos, senderos abiertos de trabajo futuro son de generalizar los resultados que presentamos acá para muchas o muchas más lógicas infecciosas tarskianas, y definir algo así como el compañero uniforme o el uniform companion de otras lógicas, digamos, infecciosas. Y otra cosa que a mí me llama la atención es que si abandonamos la regla de, por ejemplo, de left weakening vacío, ¿sí? La que dice que podemos, una vez que probamos que la conclusión es teoremática, podemos introducir cualquier conjunto en las premisas. Entonces tenemos una lógica que a la vez comparte los teoremas de la lógica clásica y cumple con el requerimiento de inclusión de variables de forma irrestricta. Pero esta lógica no sé qué, me parece súper interesante, pero no sé qué relación de consecuencia está representando y no sé, si me pueden tirar un centro ahí estaría buenísimo. Pues me parece interesante estudiar. Y bueno, eso es todo. Muchas gracias.
Muchas gracias, Agustina, por la presentación.
De nada.
Las autoras han solicitado las preguntas en inglés, entonces si por favor pueden, if you can elaborate the question in English, could be great, please. Yes, Joaquin? Oh, Bruno.
Yes, thank you for the talk, Agustina and Martina. Congratulations. And my question was is about the proof system. I would like to know if you have some completeness proof, or you have some ideas of how to do this completeness proof. And if you are not in some sense representing the formula notion of weak of paraconsistent weak linear and weak linear. So if you have that, maybe you have some philosophically interesting applications connected with inclusion of content inclusion and so on.
Yes, thank you, Bruno. I will start answering the second part. Yes, it's basically clashing everything. The proposal of the uniform companion is to clash everything to the formula level. But I think there's still value in that because maybe it's notationally it's indistinct to use a conjunction and a comma, for example, on the left side. But I think philosophically there's like an interesting point there, and it seems like everybody that's working on these logics has like a feeling that they are substructural even though they are not. And this work seems to clarify why this feeling is installed in all of us. And about the soundness and completeness of the proof systems, so you know that the first two, I tried at least to obtain them through the method of cut-free ordinary sequence calculus given there, and if followed right, it should be sound and complete, and it should have a weak cut elimination result in the sense that its cut is admissible in both. But we also have like a relative soundness not, but a relative completeness. I added here in an appendix at the end. So this is like the proof of soundness of the new restricted weakening rules. But also this one, it's always like the easy part to prove. But as to completeness, what we proved is that when, for example, if this sequence has a derivation in the paraconsistent weak-linear, not the uniform, but in the paraconsistent weak-linear system, and the variable inclusion requirement is met, then this same sequence is provable in the uniform system without using the cut rule through a transformation that we define in the proof. And with this, together with the fact that in the original one, it has the same theorems, we can prove also the completeness of this new system. Basically, you can transform every proof that uses left weakening to a proof that uses left weakening with the variable inclusion requirement or the empty set version with the bar nothing as a superscript. Yes, it's the same method used by Conilio and Corvalán in their ALK versions of with linguistic restrictions. Yes.
Thank you, Agus. Thank you.
Yes.
Okay, thank you for the answer. I think Fabio Miranda has also a question.
Yes. Can you hear me?
Yes.
Yeah, I have only a curiosity, which is not really related to your point, but when you present the sequence calculus,
yes,
you immediately say, this rule is impure because it introduces two connectives. Why did you say that? Why is it so important from your point of view? The remark.
Okay, so there is a result made that it's published that it's impossible to give like against in calculus with certain desirable properties for these logics. And what this result or non-result proves is that you have to either sacrifice the fact that one rule introduces one occurrence of one connective, or you have to abandon the fact that the comma behaves as a conjunction and as a disjunction, or you have to use certain syntactic restrictions of some sort. So what I clarified here for those who are maybe more on the who are familiar with this is the fact that what I decided to the route we decided to go with Martina is to work with impure rules. Yes.
Yeah. Can you put the rule?
Yes.
Yeah, there are several impure rules, yeah?
Mm-hmm.
But maybe, I mean, I'm asking and I'm commenting because I think these goods are really good for practice. Yeah?
Mm-hmm.
And an answer that I can give and I want to explore is that maybe they're not so impure in the sense that, as it is known, there is some point of view that says that negation is not really a connective in the ordinary sense. It can be considered as a modality. Then maybe it's not so impure at the end. That's the remark I wanted to say. That's it. Thank you.
Perfect. Thank you.
Thank you, Fabi. Okay, so if there are no more questions, then we proceed with the last talk of the session. And for this talk, is the author here?
Hello. Yeah.
Fernando,
I'm here.
right?
Hello.
Okay. Good. Then I now present Fernando Cano, Jorge, and Luis Estrada González with a work titled Logics for Progressive Reasoning. So, Fernando, please proceed.
Okay, can you see the slides now?
Yes.
Good. All right, well, thank you everyone for having me here. This is a joint work with Luis Estrada. This is called Logics for Progressive Reasoning. And the main point of the talk is that in reason giving practices, some notion of progress or non-circularity is needed. This comes from an idea in Silvan and Goddard's paper called On Reasoning. And there, this idea of non-circularity is formalized as an irreflexive conditional connective. So I'm recovering that idea from them. And in trying to pursue this kind of systems for reasoning, some properties like logical relevance and connexivity arise naturally. So I'm going to structure the talk in 3 parts. I'm going to discuss a little bit about circularity and progress in logic for a proper philosophical context of the talk. Next, I'm going to give some expansions of FDE that satisfy the ideas we are after. And finally, I'm going to do a little bit of remarks regarding soundness and completeness for these expansions. All right. So we're going to try to consider reasoning or the practice of reasoning very simply in the sense of the act and effect of putting validly some reason for something else, just giving some support to another proposition. And we're going to try to formalize these ideas in terms of conditionals. So we're going to formalize the idea of reasoning as we have it here, to claim that the AIs are or give a reason for B is going to be represented as a conditional relation between those AI, which are to be thought of as reasons, and B to be that proposition which is supported by those reasons. Naturally, in this construction, we could also have reason binding having conjunctive-like behavior, just as the reason-giving behavior here is implicative-like. So as I said, these ideas come from Silvan and Goddard's '89 paper, but there are also recent developments in this area, mostly by Krupi and Yakona. So the original paper from Silvan and Goddard advanced the idea of logics for progressive reasoning, and they were motivated by very different ideas, mostly 3 of those, which are Aristotelian conceptions of reasoning. How do we actually behave in reason-giving practices? And also, when speaking about the logics of scientific confirmation. Now, in that paper, the semantics for the progressive logics were very complicated. They mixed Raudling-Meyer semantics, which are variations or generalizations on cryptic frames, but they also use some lattice order imposed on information or beliefs, or some simple sets of maybe evidences, and that results in a very complicated semantics. What I want to do now is to give an extensional approach to demonstrative or pawnable reasoning. This means deductive reasoning, in which the conditionals we're going to talk about obey modus ponens. And this is very simpler compared to Sylvan's original semantics. And this extensional approach actually delivers the properties these authors expected from the systems. First, non-circularity, which also includes the failure of implicative forms of lattice principles, which is something I'm going to talk about a little bit more later. But also they satisfy the properties of connexivity and relevance. So the Aristotelian ideas that motivate systems we're calling progressive logics mostly arise from this Aristotelian definition of reasoning, which he called syllogismos. This is something that was discussed today in previous talks. The claim that Aristotle considered an argument, consider reasoning to be an argument in which the premises should necessarily entail the conclusion, but I want to stress that the definition he gave demands that the conclusion is different than the premises. And this is so because Aristotle was concerned with ruling out question-begging arguments. He would not endorse claims like A because A, or A is a reason that justifies A itself, because that would be a fallacy we know as petitio principii. So if we think of reasoning in terms of conditionals, it seems that Aristotle's definition of reasoning should turn away from the reflexivity principle A implies A. And moreover, since this should happen for every Aristotelian reasoning, then something like irreflexivity, the negation of self-implication, should be demanded in these systems of reasoning. And this is not a new idea. Robert Mayer and Errol Martin wrote a paper by the end of the 70s called S for Syllogism, and developed a system of implicative logic where they have this irreflexivity schema. So where we are heading is, as I said, trying to give some expansions of FDE that use simpler semantics compared to Sylvan and Goddard's, that include conjunction and disjunction, unlike Meyer and Martin's S, which as an implicative logic only used implication and was only expanded with negation by the end of that paper, but never with conjunction and disjunction. And finally, that our expansions of FDE validate unrestricted connexive thesis. This is a different result than Krupi and Iacona's approaches to the logic of reasoning have given, because they only recover conditional modal statements of the connexive principles, like the one we have here, which is a conditional version of Aristotle's thesis. And moreover, one of the expansions I'm going to present satisfactorily combines logical relevance and connexivity, which is a very difficult thing to achieve, because most of the attempts at combining these families of logics ends up validating every negative implication. So I mentioned something about lattice principles. What I mean about lattice principles is principles like self-implication, idempotence of conjunction, simplification, addition, and even the principles involving negation, like double negation, elimination, and introduction, the Morgan properties, etc. I'm going to keep all these lattice principles in rule form. That means stated with this turnstile. but I'm gonna abandon all of the versions of these principles that are stated with an arrow or with a conditional. So one of the justifying ideas behind this move is that when we think about principles like reflexivity, simplification, or idempotence of conjunction, and we put them to the test of the Aristotelian definition of reasoning, we see that the conclusions in those principles appear already in the premises. And in a sense, these are question-begging or circular schemas, because the conclusion is not different from the premises, or equivalently, we're asking for the truth of the conclusion to be given in the premises. And I will also claim that these principles are not entirely traditional, in the sense that ancient logicians and medieval logicians seldom used lattice principles. So we're going to get to the second part of the talk now, which is to give the progressive expansions of FD. I'm going to run a little bit fast in the preliminaries for FD, because I'm going to assume that most of the people already know how this logic works. Just keep in mind that I'm going to be using Don semantics, a Don semantics presentation of FD, in which we have 4 truth values that can be thought of only true, true and false, neither true nor false, and false only. And since Don semantics is meant to be a relational semantics, we can have translations of these truth values for any given formula set theoretically through membership in this way. So as we know, FDE has the same truth and falsity conditions for the connectives as classical logic does, but the fact that we can express those relationally allows us to present truth conditions and falsity conditions independently, as you can see in this slide. And we are also able to give the truth tables for the connectives instead of doing it in terms of truth and falsity conditions relationally in the following way. Now, for the proofs of soundness and completeness of the expansions of FDE, I'm going to use Chris Tableau systems for FDE, which I also will assume people have encountered before. Just keep in mind that the plus signs we have means that the formula is related to truth, and the minus signs mean that the formula is not related to truth. Okay, so when I call a logic progressive, what I mean is that this logic, first of all, is non-reflexive. So the self-implication principle is not valid. And furthermore, the reflexivity principle is a theorem of the logic. I also claim or mean that for a logic to be progressive, it should have the transitivity rule. And I generalize a bit further the ideas of progressive logic. This is something that Sylvan and Goddard didn't do in their paper. I generalize these ideas into a logic being Aristotelian, and that means that the logic is progressive, and moreover, it has Aristotle's thesis and its variant, and Aristotle's second thesis. Now, if you think about this conditional as a reason-giving connective, what we're claiming here is that A cannot be a reason for its opposite. And we also are claiming that if A is a reason for something else like B, then the opposite of A cannot be at the same time a reason for B. So these are connective theses that are motivated by reading the conditional as a reason-giving connective. As I said, I was going to give 4 expansions of FD. So I am taking the language of FD and augmenting it by 4 different conditionals, which are actually adaptations or variations of the Filonic conditional from EFDE, Mortenson's conditional from M3B, and Paris analytic implication. So in the first case, the first expansion, the conditional we have here has the same characteristics of the one we find in EFDE and Mortenson's value, Mortenson's conditional. But the difference is that in order to make the conditional being irreflexive, I introduce this only false value in this part of the matrix. And this gives me the ability to give some truth and falsity conditions for the Tableau system as well. As you see, I'm summarizing some of the effects of these rules in terms of disjunctions or conjunctions, just to make the tree a little bit more compact. But some of the conditionals have this weird property of being always false. So if we return to the table of this conditional, you can see that the false value 0 appears everywhere in the table. So that means that the conditional we're giving here is always going to be false, or the negation is always related to the truth, which means that the conditional is false. So it's going to be false whenever A is true or A is false, B is true or B is false, A is not true or not B is not true, etc., etc. And when we say that the conditional is not false, that results immediately in a contradiction or in a closed branch, because the conditional is always false. So that's the first expansion. A little bit unsavory because of this negated implication being valid every time. The second expansion, which is the best of the 4 systems I give, only modifies the previous conditional in this part of the table. And this little change makes the big difference of avoiding the problem of validating every negated implication. So it also has its Tableau rules, but in the case of falsity, we see that we don't have the problem of validating negated implications as we did in the first expansion. Now, the first 2 conditionals explore the case in which we introduce a valuation 0 in the last corner of the table, but the third and fourth conditionals explore the case in which we do the same thing, but in this part of the matrix. So we get a third conditional in this form, but this third conditional is going to have the same problem as the first, which is it's always going to be false. And whenever you reach a node of this form, the branch is going to close, because it's never the case that conditionals are not false in the third expansion. And finally, we combine these 2 strategies that we have discussed so far, which are putting an empty value here and putting a 0 value here. And that will give us the 4th expansion of the logics I'm giving here. And as you can see, we avoid the problem of validating negated implications. So in general, our conditionals are not readable as conjunctions or biconditionals, which is a problem that sometimes connected logics or attempting to design connected logics face. All the conditionals enjoy modus ponens, modus tollens, and conjunctive syllogism, which is nice. Only the third has contraction, prefixing, suffixing, and conjunction, disjunction, composition. And only the third and fourth have reductio and weak forms of contraposition. As I defined Aristotelian logics, we see that the 4 expansions are Aristotelian. but only the fourth expansion is not connected because it does not have Boethius' thesis. The other three have Aristotle's thesis and Boethius' thesis, which makes them connective systems. And an interesting feature of the logics is that no paradoxes of implication are valid. Whatever paradoxes of implication you can find in the literature, those are going to be invalid in the 4 expansions I gave. Currently, I'm trying to give a proof determining whether these logics have the variable sharing property. But this is work for the future. And as I mentioned, the second expansion is special because it avoids validating all negated implications while also combining connectivity and relevance in a nice way. Finally, in the paper, we already proved soundness and completeness for these 4 systems. And the way we did that was simply using the general techniques from Graham Priest, which basically rely on defining faithful interpretations for branches of the tableau, proving a soundness lemma, from which immediately a soundness theorem follows. And in this case, something interesting happens with the conditionals that validate negated implications, or which are always false. Because, for instance, since an interpretation is faithful to a branch, then when we're talking about this kind of rules, then the truth is not in the negation of the implication, which means that falsity is not in the implication, but this is never the case. So that means that the branch closes because we saw that the rule automatically closes those branches. And then since the hypothesis is that sigma is faithful to the branch, we can follow the results. And this also happens with the other conditional that has the same properties just discussed. And in the case of completeness, again, we use Priest's techniques. In this case, we define these interpretations that are induced from open branches, and we give a completeness lemma that allows us to reach a completeness theorem. Again, the conditionals which validate negated implications, or which are always false, have an interesting case in the proof, because in this case, what is going to happen is that this kind of rules for the negated implication close the branch, and since the induced interpretations are only for open branches, then this case falls out of the scope of the lemma, and similarly for the other implication. And as final remarks, if we're trying to give a logic of reasons, then it makes no sense to validate negated implications. How could we have a logic of reasons if nothing is a reason for something? So that means that the second and fourth expansions of FDE we have given today are the more adequate systems. And in the original paper, Sylvan considered Boethius' thesis to be optional. So we can think of Peer4 as still a very attractive system, even if it is not fully connected. And finally, since we don't have lattice principles and these logics validate very, very few things in terms of implication schemas, we could think of more powerful progressive logics if we try to combine the reason-giving conditional with other more usual implications like material implication or some relevant-looking implication like those of RM3 or maybe EFD And that's it. Thank you.
Thank you very much, Fernando. So we have time now for some questions. So yes, Joaquin, please.
Oh, thank you. I really like the talk. I have more like a curious question. If I understand well the project, you or this kind of logic wants to recover like everyday practice of reasoning. And how do you think that it would be it would behave one of these systems if you extend the vocabulary to more expressive language? I don't know if it is suitable to extend it to first order, but perhaps something lesser than that. So what do you
Right.
think about that?
Yeah. So far, I've only experimented with propositional or zero-order languages. In trying to generalize this progressive logic idea to Aristotelian logics, as I did, I do mention in the paper that when we go into first order, schemas that are classically invalid, like subalternation, which was very important in syllogistics, can be validated if we follow the formalizations that McCall has given, for instance. So I know that the first order versions of these systems are going to have very interesting contraclassical thesis as well. And in terms of expanding the language with other connectives, I have only considered so far to introduce, as I just mentioned, maybe material implication or maybe other sort of well-behaved conditional, just so that I can have a stronger logic in the sense that if we, as you said, if we want to model everyday reasoning, then most likely we're going to need to have things like simplification or yeah, maybe even addition or other kind of schemas that inside of them have some reason giving implication. Examples like, well, this person is saying that A is a reason for B, and they are also saying that B is a reason for C. So in particular, then we conclude with maybe material implication or other implication that A is a reason for C. Things like that, which try to combine those two conditionals and other connectives. In the original paper of Sylvan and Goddard, they explore a little bit this idea, and they choose to do this combination with a relevant arrow that obeys the Raudley-Meyer semantics. I think that would be the better way to go. But as I said, I'm currently exploring the extensional approach or the simpler semantics as a first step in trying to develop these logics. But I'm really interested in trying to develop systems that could actually be implementable in practice.
Okay. Thank you, Fernando, for your answer. So I don't know if anybody else wants to comment something or to have a question. Okay. Well, then I would like also to ask you something. Yeah, I agree with Bruno that your proposal as a general theory of reasoning is very interesting. Yeah, and you give a lot of philosophical motivation about your work. What I would like to know if you can comment some motivation, some practical motivation about connectivity or connective logic. In particular, what the few I know is that there's a relation about default reasoning and connective logic. So I don't know if you can comment something on this direction.
Yeah. So connectivity here, as I mentioned, arises when you try to read the conditional as a reason-giving connective. So it sounds like it should be valid in this context to say that something cannot be a reason for its opposite, you know. But as I also mentioned, this reason-giving logics are meant to be a framework for other sorts of practices like scientific confirmation. So in scientific confirmation, we have a very interesting example, which is consider a hypothesis A and think of the reason-giving implication as an evidence giving or as a support in evidence giving connected. So in a sense, when we talk about logics of evidential reasoning or logics of confirmation in general, we're thinking that some hypothesis should not confirm its own negation. And also that if a hypothesis confirms something else, then that same hypothesis shouldn't confirm the negation of that something else. And if you think of both examples, you can naturally see that they are translatable to the connective principles called Aristotle's thesis and Boethius' thesis. And all these ideas with philosophical and scientific motivations were explored by Richard Sylvan in very different papers. And at first, it was very interesting for me to see that he could justify the introduction of connective thesis with such a natural reading of the conditionals. We have to keep in mind that these conditionals are not only restricted to ideas of truth preservation, they are also trying to encode a support relation in the sense that how supportive is an antecedent for a consequent. They also explore these ideas of reasons being given, being advanced to something else in a way that they are supportive but not conclusive. For instance, think like, I don't know, maybe running is a reason, sorry, being healthy is a reason for going out jogging or running, but that doesn't mean that whenever you want to be healthier, you're going to go out and run, because maybe that's not a deductive situation in the sense that the truth of the antecedent doesn't need to imply the truth of the consequent. It's just that there's some sort of support given from the antecedent to the conclusion, in the same sense that in science we have some observations that support some hypotheses, but not conclusively demonstrate that they are actually true. They sometimes make them just more likely to be true. So even when you think in those terms, the connective way to read these implications or these reason-giving or evidential supporting conditionals keep holding. So these are interesting ideas in the relations between logic and philosophy of science.
Yes, I agree. It is very interesting that direction. a very general intuition I have about these terms of connectivity is due to the one thing you mentioned at the beginning is the relation with Kripke semantics and modalities, and well, there are a lot of motivation and applications. For instance, in computing, where I am a little bit more familiar, and because for instance, in computing, it is very natural to reason in some sense with some logic, non-classical logic, because the particular context of computer systems. In a talk just before, we were talking about blockchain systems and zero knowledge proofs, which are it's a way to reason where we know that there's a proof or something, but we actually do not have a proof of that. So I think that because of my experience in computing and model logics, I think this kind of reasoning would be very fruitful in that direction.
That's great. I would like to look at the details and discuss a little bit more. If I can say that these reasoning logics are also implementable in computer science, then that's even better. Yeah.
Okay. Thank you. Thank you, Fernando. I don't know if somebody wants to comment something else. Okay. If there are no more comments, then I thank again to Fernando, and also I want to thank everybody here. I am very grateful to all of you because you made possible this event. So I don't know if anybody else want to come in, want to comment something about closing the event. Maybe Lourdes and Fabio, who are also organizer. Miguel also is here, is also an organizer.
Please go ahead.
Yo en español solo voy a comentar que me gustó esta sesión o estas sesiones y que agradezco a la gente latinoamericana por estar aquí. Ayer con Mauricio pues fue especial que él estuviera aquí con nosotros porque justo él es de las personas que ha permitido que este evento exista y que ahorita estemos aquí reunidos y reunidas. Y yo espero que próximas sesiones también haya más presencia femenina en algún punto o presencia de otras, no solamente masculina, sino también femenina. Los que estuvieron escuchando hoy a la doctora Aldeco, pues espero que les haya gustado y también que haya este incentivo por que los estudiantes, las estudiantes, les estudiantes nos acompañen más y que este sea un espacio para que todos podamos platicar, para discutir, tener retroalimentación y apoyarnos entre todos. Gracias.
Ok, yo también quiero agradecer a todos los que estuvieron involucrados en este evento, tanto organizadores como aquellos que se dedicaron a revisar los resúmenes en extenso y así también el público gustoso que estuvo aquí con nosotros. Les agradezco mucho, espero que les haya gustado este evento que es para ustedes y el contenido pues es también para ustedes, para que puedan hacer sus trabajos un poco más robustos. Les agradezco de todo corazón. Muchas gracias.
Muy bien, pues muchas gracias a todos. Con esto concluiríamos el evento. Nada más me gustaría como comentario final mencionarles que en la página del sitio van a encontrar las grabaciones de todas las participaciones para que puedan consultarlas Eventualmente también nos gustaría tenerlas seccionadas por plática, entonces en un futuro cercano para que sea más cómodo la exploración y también pues estaríamos considerando, ¿no? Los vamos a invitar sobre un segundo llamado para publicación de un artículo completo, entonces si hay interés, pudiéramos considerar esa posibilidad, pero pues todas esas comunicaciones se darán en un futuro cercano. Las constancias de participación también están trabajándose, ¿no? Entonces se las haremos llegar de manera electrónica, a reserva de que alguien la solicite de otra manera. Gracias. Hasta luego.
Gracias a todos, todas.
Adiós, adiós. Gracias a todos.